Okay, thank you very much, Helmut. It's great to be here. Thank you for the invitation. So this is going to be a report on joint work with Nick Sheridan, who's here. So this is a mirror symmetry talk, and mirror symmetry is just coming up to its 25th birthday. It's been around for a while. It's something that came out of string theory, and in terminology that we sort of inherited from string theory, it relates the so-called A-model geometry of one Calabi-Yau manifold, X, really some Calabi-Yau manifold with some extra data, to the B-model geometry of another called X check. So the A-model concerns the symplectic aspects of the situation, symplectic aspects of X, while the B model concerns algebrogeometric or complex analytic aspects of X check. So still using this sort of stringy terminology, so we have open string invariants. So on the A side we have Fukaya categories. Those are open string because they involve maps from Riemann surfaces which have boundary into X. And on the B side, you have derived categories of coherent sheaves. Their connections with open Riemann surfaces are a little less clear, but there's some sort of conformal field theory going on in the background. And then so-called closed string invariants. So on the A side, quantum cohomology and counts of pseudo-holomorphic curves. So I'm thinking now of maps into your symplectic manifold whose source is a closed Riemann surface. And on the B side, things like de Rham cohomology, Gauss-Manin connections in sort of families of varieties, periods of a holomorphic volume form. So it's supposed to be the case that mirror symmetry is involutory. So the mirror to the mirror is your original Calabi-Yau, with these two sort of aspects of the situation exchanged. In my presentation, that symmetry, which gives its name to the subject, will be disguised. The data on the A and the B side will appear to be somewhat asymmetric. That's illusory, or at any rate it should be, and it comes up because I'm only going to show you part of the data, the part that I need for the symplectic geometry on the A side and the algebraic geometry on the B side. So this is a sort of brief summary of where I'm going. So we're to consider a mirror Calabi-Yau pair. So X will be some symplectic manifold. The key Calabi-Yau property will be the vanishing of the Chern class of its tangent bundle. While X check, I've used a script X because it's a somewhat different sort of beast. This is going to be a smooth projective algebraic variety with trivialized canonical bundle. That's the Calabi-Yau condition. And now the open string version of mirror symmetry, so homological mirror symmetry, as formulated by Kontsevich back in '94, claims that the categories that are associated with these two sides should be equivalent. So the Fukaya category, f of x, or some derived thing of that, should be equivalent in some precise sense to the derived category of coherent sheaves on X check. So these days we know a lot of mirror pairs. There are very few of them for where we actually know the homological mirror symmetry is true, though the list is gradually growing. Thanks in particular to Nick. So what we're going to do is this. We're going to suppose some partial fragmentary form of homological mirror symmetry. We're going to suppose that you have some subcategory A of the Fukaya category and some subcategory B of the derived category. And we're going to suppose that you've proved the fragment of homological mirror symmetry that says that those two subcategories are equivalent in the appropriate A infinity sense. And furthermore, B should be reasonably large. Namely, it should generate, in a certain sense, the derived category. So from that assumption, which we think will be relatively amenable to checking in geometric examples that are under study, under that assumption, we'll be able to deduce the full strength of homological mirror symmetry. So these categories in their entirety are equivalent. And that's the open string part of the picture. We'll also be able to deduce not the whole story, but a good part of the story of closed string mirror symmetry. Namely, we'll be able to say that the quantum cohomology of X is isomorphic to the tangential cohomology of X check. That's the cohomology of the sheaf of polyvector fields, so the sheaf of exterior algebras on the tangent sheaf to X check. And that isomorphism will preserve a certain amount of interesting structure, which will tell us that certain counts of rational curves in X are equal to certain periods of, roughly periods of the volume form on X check. Yes?
So you're fixing X here? Or?
Yes. So you should just imagine that the details will follow, but just imagine that someone has handed you this pair and X and X check and told you that this fragment of homological mirror symmetry holds.
And then from this
We'll deduce the full strength. We'll deduce this equivalence of categories, and furthermore some closed string stuff. And I should say at the outset that we get some equality of counts of rational curves with something on the other side. We're not quite at the point where we can actually use this to count curves, because there's a certain, well, essentially the normalization of the volume form is treated a little unsatisfactorily in what we do, so we're working on it so that this becomes sort of practical. Okay, so now I'm going to try and now I'll spend a while trying to make all this precise, somewhat more precise anyway. So let me start on the A side. So here's the symplectic geometry setup. Okay, so sort of boring name. I'm going to call an integral symplectic Calabi-Yau manifold the following data. So you have a compact manifold X of some dimension 2n with a symplectic form on it, first of all. But more than that, you have some symplectic submanifold D of codimension 2. And in the complement of that submanifold, your symplectic form is exact, and you're given a primitive theta for it. So omega is d theta away from d. Okay, so, and furthermore, the Calabi-Yau condition is that you have a complex volume form on your manifold. That's just a C infinity trivialization of the canonical bundle. So this setup tells us, well, it tells us that the first Chern class is 0 because you have this complex volume form. And it tells you that it constrains the cohomology class of your symplectic form because it has to be a multiple of the Poincaré dual to D. So it's up to a multiple, it's an integral cohomology class, and that's certainly a restriction. So,
sorry.
Yes?
Given Calabi-Yau manifold, does there exist such a divisor in general?
Well,
That's why it's probably one of the complements like forms exact.
It depends a bit what you mean by a Calabi-Yau manifold, but I basically no. But you have data like this if you have a projective Calabi-Yau manifold. You see that. So the main class of examples is that I have in mind is the following: you have a complex manifold X. you have a Hermitian holomorphic line bundle over it, and the Chern connection has positive curvature omega. So D is the zero set of some holomorphic section. Theta is the Chern connection expressed in the trivialization defined by S away from its zero set. And omega is a holomorphic volume form. Now, by Kodaira embedding, all this data can be taken to be pulled back via a holomorphic map from X to some projective space. So really, so we're talking about projective Calabi-Yau manifolds here. So that will be the kind of gadget that I'm going to put on the A side of mirror symmetry. I should caution that, you don't expect such a thing always to really have a mirror. If you take a sort of a healthy, upstanding member of the Calabi-Yau community, it probably won't. It's only going to have a mirror if it's just on the brink of degenerating horribly. It needs to be about to degenerate to something very singular. And really, one might put that degeneration as part of the given data, and I'm suppressing that. Okay, so that's the A side. The setup on the B side is going to be this. So let's introduce the field K of finite-tailed Laurent series. That will appear throughout. It's a field. So in the world of algebraic geometry, you should think of K, or its spectrum, as a sort of punctured disk, a formal analog of the punctured disk.
I don't think you really mean what you write, the Laurent series field.
I don't?
I mean, you could have the series in Q whose nth coefficient is Q to the minus n factorial. That's not what you write. That has infinite combinations. You want the Q inverse on the other side.
I see. Yes, I beg your pardon. Thank you. Yes. Yes. Okay. Okay. Thank you. Okay. So this is some sort of formal punctured disk, and a reason to make that identification is this. K is the home for Laurent expansions of holomorphic functions on the disk with a pole just at 0. So what you should think of is that maybe you have some kind of holomorphic function, and we're just recording it via its Laurent series. So okay, so the sorts of Calabi-Yau varieties that we'll be considering on the B side will be smooth, n-dimensional, projective algebraic varieties over the field K. That's a perfectly sort of reasonable notion. This is a field. And they'll be equipped with, well, it's not quite the right term, but holomorphic volume forms, trivializations of the canonical sheaf, omega check. Nowhere vanishing holomorphic top forms. Okay. So, what you can think here is, so imagine that X check is defined by homogeneous polynomials, some finite set of homogeneous polynomials whose coefficients, those are elements in this field K, their Laurent series. Imagine they all have positive radius of convergence. Well, then you can turn X check into an actual holomorphic family over an actual punctured disk. So, for instance, imagine if you have this sort of this elliptic curve, you have y squared is x cubed plus ax plus b, where a and b are in the first place Laurent series. Well, if they happen to have positive radius of convergence, then rather than just thinking of this as an algebraic equation, you can instead evaluate those series and think of this equation as cutting out some complex subvariety of a disk cross CP2. So, we'd be sort of taking So in the other direction, you sort of take this thing sitting inside delta star r cross CP2, and basically you take its Laurent expansion, and that's our variety over K. Okay? So we're not actually going to assume convergence of our series. For that reason, we will work in this algebraic setting. Mirror symmetry suggests that convergence should, in this sense, should be the case, but it's hard to prove in typical examples, and so we don't want to assume it. Okay, so sticking on the B side, so this is a bit about monodromy. So the algebraic way to say this is that you have the algebraic de Rham cohomology of x over k, x check over k. So that means that you form the algebraic version of the de Rham complex, so that's some complex of sheaves, and then you take its cohomology, its hypercohomology. Okay, so it's closely analogous to the classical de Rham complex. So it's a graded algebra over K, and it carries an automorphism T, which is the monodromy around this punctured disk, the monodromy of some algebraic connection, the Gauss-Manin connection. So what you can think here is, so if you imagine that this X check is indeed the Laurent expansion of a holomorphic family with fibers X check Q that are complex manifolds, then what we're doing is that we're taking the monodromy around the boundary of the disk, acting in the singular cohomology of those complex manifolds with K coefficients. So it's been known for a while that the monodromies of these projective algebraic families have a very special form. So up to a base change, a substitution, Q goes to Q to the K, the monodromy is unipotent of exponent n plus 1. N is the dimension. Okay, so T minus I to the n plus 1 is 0. So I hope my references here are reasonable. So Griffiths, Landman, Grothendieck, and Nick Katz, I think, gave a nice proof in the purely algebraic setting. Right. I see. So you could think, for instance, of a Lefschetz fibration, a non-degenerate critical point, where the monodromy is a Dane twist, in which case T minus I will squish the whole of the cohomology to the line spanned by the vanishing cycle, and then T minus I will kill that. So T minus I squared would be 0. So it's going to be important for us to assume that, unlike the Dane twist, you have the following maximal unipotent monodromy condition. It's that, well, T minus I, so we've done this base change if necessary. So T minus I to the n plus 1 really is 0, but T minus I to the n is not. And roughly what that means, if you think of your family as a punctured disk in Calabi-Yau moduli space, then with the puncture sort of really mapping to some sort of singular Calabi-Yau, then that singular Calabi-Yau is as degenerate as it possibly could be. You should think, for example, of a Calabi-Yau hypersurface in projective space degenerating to something singular, but not only to something singular, it's actually degenerating all the way to just a union of hyperplanes. Okay, so that's for us, that will be an assumption that's built in. That's reasonable in this context. In fact, this is a condition that you need to satisfy in order for X check to have a mirror X that satisfies the demands of sort of Hodge theoretic mirror symmetry. So we're not, in some sense, we're not losing generality. Okay. So now back to symplectic stuff. Okay, so I'm going to talk about the so-called closed string invariants, and the key closed string invariant on the A side will be small quantum cohomology. Okay, so QH of X. So additively, that's just the cohomology of X with coefficients in this Laurent field K. Multiplicatively, it's going to have the quantum product, which deforms the usual cut product in cohomology. Many of you will know it. So the structure constants for the multiplication in this algebra are counts of maps U from S2 to X. You fix some almost complex structure in X compatible with your symplectic form. You look at maps from the two-sphere to that. They're going to have three points which are going to be constrained to lie on certain cycles. So these maps are going to be, did I say they're going to be pseudo-holomorphic? Their derivative is going to be J-linear. Moreover, we're going to weight them with powers of Q, and the power of Q that comes in is Q to the intersection number with D. So we track how many times these things hit our chosen divisor D, and that determines the exponent of Q in which they count. So that's the symplectic area, essentially. So for this class of manifolds, quantum cohomology is kind of medium difficulty to set up compared to other symplectic manifolds. It's not the easiest case, but it's certainly not the hardest. There's a very nice account, for instance, by Helmut with Salomon in this sort of setup. So the fact that C1 is 0 helps you. It also affects the algebraic structure. It makes your algebra graded. So you have this associative graded, unital graded commutative algebra. And it has one other important datum, which is a trace map, so integration from top quantum cohomology to your ground field. So that's just ordinary integration. And that trace map makes quantum cohomology into a Frobenius algebra. That's to say that the sort of Poincaré-like pairing of QHI with QH2n minus I, where you just multiply them and integrate, is a perfect pairing for each I. Okay, so that's the structure on the A side. The B side counterpart is the following. So it's tangential cohomology of X check. So that's to say it's the total cohomology of the exterior algebra on the tangent bundle, tangent sheaf. Okay, so this is again a graded K algebra. So you can multiply because, well, you can wedge together polyvector fields, and you can combine that with the cut product in cohomology to get a graded algebra structure in this. It's again a Frobenius algebra, but that's because we have this volume form omega check in play. So omega check determines a trace map from top tangential cohomology to the ground field, an isomorphism that makes this Frobenius. So it makes the multiply and trace pairing non-degenerate. So let me tell you what the trace map is, and I'm going to tell you this in complex analytic rather than algebraic terms. There is an algebraic definition. So instead of Dolbeau terms, you take this element in top tangential cohomology, and you give some sort of Dolbeau representative of it, which involves a kind of a form component and a tangential component. So that depends on this parameter Q. We're sort of thinking of that as happening on each fiber X check sub Q. you can contract it with the volume form on each fiber. And if you think that through, what it gives you, this one here is a 0, n form on the fiber. On the other hand, the volume form is an n, 0 form, so you can wedge them together and integrate and get a number depending on Q. So that's a function of Q, a holomorphic function of Q, and that's our trace. So that, or the algebraic counterpart to that process. Okay. So there's one other little bit of juice in these invariants which hasn't been exploited too much before, but is important for us. And it's that they carry distinguished classes of degree 2. So namely, on the symplectic side, well, you have the class of the divisor D, so that's codimension 2, so it's in second cohomology. Up to a multiple, it's the class of the symplectic form. And notice, by the way, that if I take its top quantum power, well, I get the top classical power plus higher order terms. And so in particular, I get a non-zero series because its leading term is non-zero. So the corresponding gadget on the B side will be the following. So it's going to be the Kodaira-Spencer class. So that's going to be a class in H1, first chief cohomology of the tangent bundle, which sits inside the second tangential cohomology as a direct summand. So this is Kodaira-Spencer for the in the direction of the vector field Q d by dq on the punctured disk. So so this is a sort of standard gadget from deformation theory. One way to say it is this. So if you think of X check as coming from a map from a holomorphic map from a punctured disk to Calabi-Yau moduli space, sort of pulling back a universal family, then the Kodaira-Spencer class is the derivative of that map, essentially. So it's describing the sort of deformations. Again, of course, there's an algebraic way to say it. And now, okay, so we're going to make an assumption which, at least a priori, is slightly stronger than maximally unipotent monodromy, and it's this. If you think of theta, the Kodaira-Spencer class, as sitting in tangential cohomology, and you take its top power, theta to the n, so that lives in the top cohomology of the top exterior power of the tangent sheaf, that should be non-zero. Okay. So in the complex analytic case, if we have this complex analytic model in play, then in fact that's a consequence of having maximally unipotent monodromy. The proof uses existence of mixed Hodge structures in the limit as Q tends to 0. We're not totally sure yet whether that's also the case in the algebraic setting, though we strongly suspect that it is. So we impose this condition in close analogy to this one, which we already have on the symplectic side. Okay, so those were closed string invariants. So now to open ones. Okay, so we have the Fukaya category relative to D. So I'm going to be awfully brief here. So this is an A infinity category. So it has structure maps of all orders. It's associative up to sort of coherent higher homotopy. It's linear over K. So the crucial thing is that its objects are Lagrangian submanifolds of X. More precisely, they're going to be exact Lagrangian submanifolds of the complement of the divisor D. So we have an object is an n-dimensional L embedded in the complement of D, And remember, we had this primitive, I'm overloading notation, I see. So theta is the one form, the primitive of omega on x minus d, and its restriction to L should be exact, d of some function defined on L. If you differentiate that condition, you see that L is Lagrangian. But it's more than that. It's an additional constraint that it should be exact Lagrangian. So these exact Lagrangians come with a few topological decorations that I won't specify. The morphisms, well, so rather than saying what a morphism is, you say what the morphism space from L0 to L1 is. It should be a K vector space. And that's Fleur's cochain space. So at least if L is transverse to L1, it's relatively easy to say. It's freely generated over K by intersection points of L0 and L1. So a morphism is a formal linear combination of intersection points between L0 and L1. There are then these A infinity operations, which include a differential on this one and a composition, and then higher associativity terms. And those are defined in terms of holomorphic polygons. So it means maps U from a disk with boundary punctures into X. So J holomorphic. The boundary intervals are labeled by Lagrangians, and you must map those boundary intervals to the chosen Lagrangians. So, you know, the technical foundations of Fukaya categories are notoriously complicated because of transversality problems. So what I learned from Nick's thesis is that by working exclusively with these exact Lagrangians in the complement of D and in this Calabi-Yau setting, you get a very large saving in foundational complexity. So, as it were, classical transversality theory is all you need to set this up. It's also really no loss in data in the mirror symmetry setting. On the B side, counterpart is the derived category. So we think of that as a differential graded category, a DG category. We call it perf check for perfect complexes. So a DG category is a kind of A infinity category, relatively simple kind in some sense. So in this case, the objects are going to be finite length complexes of algebraic vector bundles of finite rank. Locally free sheaves. The morphism spaces, well, it's almost correct to say that the morphism spaces are the X groups, the derived homomorphisms from E to F. So there's some version of sheaf homomorphisms, but actually what we're going to do is, at least one model for this, is that we'll take the morphisms to be a check cochain complex that computes derived homomorphisms for you. So we fix some open affine cover, which ultimately won't matter, and we write down the complex that computes X groups rather than the X groups themselves. Okay, so there's a differential in this cochain complex. You can compose maps. You get this DG structure. Okay. Again, there's another bit of juice which it's important to exploit. And that's some form of cyclic symmetry in these categories. So called a weak Calabi-Yau structure. That's one name for it anyway. So if you have a category C, a linear category C, A infinity category. So a weak Calabi-Yau n structure is the following. So you can regard a category as a bimodule over itself. So okay, an algebra is a bimodule over itself. So what you have is an isomorphism from that bimodule to the dual bimodule with some degree shift called beta, and that map is itself self-dual. Okay, so it's a bit like, it's pretty closely analogous to symmetric bilinear forms, non-degenerate symmetric bilinear forms on vector spaces. So that would mean an isomorphism from a vector space V to its dual, which is itself a self-dual map. So it's some categorical analog of that. And so the Fukai category has this structure quite intrinsically, no additional choices. And that's an elaboration of the fact that L0 intersect L1 is one and the same as L1 intersect L0. You have that kind of transparent symmetry. This one gets elaborated first of all to an isomorphism of Floch homology. I beg your pardon. That's the cohomology of the HF is the cohomology of the Hom space from L0 to L1 to a shifted dual of the Homs from L1 to L0. Okay, so that roughly speaking, that expresses this fact. And this Calabi-Yau n structure is a further elaboration. So you have the same structure on the derived category, but now it depends on the choice of the volume form. It's not intrinsic to the variety, and it's Serre duality. So now we come to homological mirror symmetry. So let me preface it by saying that, people working in mirror symmetry identify for us mirror pairs of Calabi-Yau varieties. They have criteria for saying that they are mirrors. Some of those constructions are relatively simple, like constructing a mirror to the quintic threefold. And some of the recent ones are pretty sophisticated. So the Gross-Siebert program is a huge machine that produces mirrors for you. But there's some geometric process that will identify these mirrors, and I'm going to just treat it absolutely as a black box for present purposes. Just want to be clear that I'm not trying to say something circular. There is some criterion out there. So Kontsevich's homological mirror symmetry conjecture, a version thereof, says that in that situation, your Fukai category and your derived category should be equivalent. So you should have this A infinity equivalence respecting these weak Calabi-Yau structures. So I've underlined this relative Fukai category. So my underline is just a notation to say that there's some annoying formal process of an algebraic enlargement that you have to do to turn the Fukai category into something which has the same sorts of formal properties as this one. And I don't really want to spend time working it through, other than to say that it's a completely algebraic and not geometric process. Okay, so that's its derived business. Okay, so that's the conjecture. Okay, so we're going to be assuming some fragment of this that I call weak homological mirror symmetry. So that's to say, we're going to imagine that in X we've got some selected Lagrangians. So they form some full subcategory A of the Fukai category. And we suppose that we've got some selected sheaves forming a full subcategory B of the derived category. And furthermore, that category B has to be reasonably big. Namely, it has to split generate the whole category. Come back to that. And we suppose that we've proved homological mirror symmetry for those subcategories, which is to say, we've got this A infinity functor from one to the other, respects this weak Calabi-Yau structure, and at the level of the cohomology of the Hom spaces, it's a categorical isomorphism. So split generation, that means that you start with the object in B, and now you're allowed to do various formal things to them. You're allowed to shift degrees. You're allowed to take mapping cones of maps between them. You're allowed to pass from an object to a quasi-isomorphic object, and you're allowed to...
Understanding what, we can construct a lot of algebraic objects, but some of them actually reflect something geometric and some others.
Well, so that's the case on the Fukaya category side. So so if you pass to a direct summand in an endomorphism space in a Fukaya category, its geometric meaning is dubious to say the least. But on the algebraic side, it's actually you will always get an honest complex of sheaves when you do these things.
It's typically difficult to go from understanding this formally completed category to classifying Lagrangian.
Correct. Yeah, I mean, of course, that's, yeah, I mean.
But how far is it perhaps that we consider this category is just not enough objects? Maybe
So that, yeah, so you could, I mean, there's this old proposal that you should introduce these coisotropic branes or something and try and introduce more geometry. Seems very, I'm a bit skeptical. It seems very difficult to do in general, and the algebra is a very much more efficient process. There is at least, so this business of passing to direct summands, there is at least a measurable thing that you need to do to kind of get from the formal version where you pass to direct summands and the one where you do not. It's detected at the level of Grothendieck group, so one can really, in future, one could hope to kind of pass from these annoying summands in endomorphism spaces to at least formal combinations of Lagrangians. Let me just point out that so you can imagine that you could take for this reasonably large subcategory B the following rather simple thing. So you just take the structure sheaf O. We had a projective variety, so you have this very ample sheaf O of 1 and its powers O of 2 and O of 3 and so forth. And they do split generate this derived category. So what you should think of perhaps is that you've identified a collection of Lagrangians which are mirror to the structure sheaf and these O of n, and that you've identified those parts of the categories completely with the A infinity structure. That's really quite a reasonable thing to ask in the context of the Gross-Siebert program, though of course it's not easy. Okay, so yeah.
Statement that coherent sheaf has a finite resolution by method of
This statement, yes, it follows from that and actually I think it follows from the I think there's a bit more to it than that. I think one starts with identifying generators for the derived category of projective space, so Bailenson generators. And then you say that you argue, so Bailenson tells us that these things generate the derived category of projective space, and then you argue that they're derived restrictions to a subvariety again split generate. And that argument indeed involves finite resolutions. Okay, so here's our results. So on the symplectic side, we have one of these integral symplectic Calabi-Yau manifolds, dimension 2n. On the algebraic side, we have this n-dimensional smooth projective variety over the Laurent field with a volume form. We have this maximal degeneration assumption, which is that the top power of the Kodaira-Spencer class is non-vanishing. And let me remind you that in the analytic setting, that's a consequence of maximal unipotency of the monodromy. Okay, so suppose you know weak homological mirror symmetry, so you have this isomorphism between these subcategories A and B, where B is large enough to split generate. Then you conclude the following. So A split generates the Fukaya category. So all your Lagrangians are built in some formal sense from the ones that you studied. And as a pretty immediate consequence of that, full homological mirror symmetry holds. That's to say, the derived Fukaya category is quasi-equivalent to the derived category of coherent sheaves by a functor that extends psi. Second, there's a canonical isomorphism kappa of the quantum cohomology algebra of X with the tangential cohomology algebra of its mirror. And that isomorphism preserves the special degree 2 element. So it sends the class D in quantum cohomology to the Kodaira-Spencer class theta in tangential cohomology.
But you said that it would not be enough to find what the coefficients are of this quantum cohomology problem.
No. No, so hang on. So one moment. So yeah, I mean, so the third clause is the numerical part. So okay, so psi. So it also, excuse me, that this psi here should say kappa. I beg your pardon. That's this isomorphism. It also preserves the trace maps, the Frobenius algebra structure of these algebras. And consequently, you can try and get numbers out. So, namely, if you take the top power, quantum power of the hyperplane class D and integrate it, you get the same thing as the trace with respect to the volume form of the top power of the Kodaira-Spencer class. Okay, so let me spell that out a bit, including the caveat that Helmut is alluding to. So that, so this trace of the theta to the n, it means that you're in analytic language, you're taking the volume form, you're wedging it with its contraction with theta to the n and integrating down the fiber to get a holomorphic function in Q, and then you take the Taylor series of that. And that's equal to this thing, which counts certain curves. So the caveat is that this is not yet in practical form for actually counting curves, for example, on the quintic threefold. And the reason is this. So, of course, for this equality to be true, you have to normalize your volume form correctly. You could multiply it by some holomorphic function in Q. So if I go back, where was that hidden here? So it was hidden back here. So this A infinity functor respected weak Calabi-Yau structures. It means that it intertwines the sort of Poincare duality on Floer cohomology with Serre duality in the derived category. Okay, so that's a kind of mirror symmetric normalization of the volume form. And that's the one that we're using here. Now, Hodge theoretic aspects of mirror symmetry tell us that there's a correct normalization of the volume form which is determined entirely on the B side, and that's the one we should be using. But we haven't yet proved that. We're working on it. If one had that, then you can actually hope to count curves. So long as you know precisely what the mirror map is as well, but that's somehow part of the same story. Okay, so let me just tell you how the argument for the first clause, let me return to the theorem. So let me discuss split generation of the Fukaya category by this subcategory A. Okay, so now there's this key player which whose entrance has been sort of long delayed, and that's a closed open string map. So it's a ring map from CO, from quantum cohomology to something categorical, namely the Hochschild cohomology of the part of the Fukaya category that we're looking at. Okay, so Hochschild cohomology is natural transformations from the identity functor to itself. There's some sort of long story there, but geometrically this involves. Well, let me just sort of modify this picture a little. It involves looking at things that are very like the maps that go into the definition of the Fukaya category, but there's one extra thing, which is an interior marked point on your disks, which is constrained to lie in some chosen cycle C. So C is in quantum cohomology, represents a class in quantum cohomology, and what CO of A counts involves, some sort of elaborate definition of Hochschild cohomology, but ultimately it involves counting pseudo-holomorphic maps like this, Lagrangian boundary conditions, and this interior constraint. And so it's been known for a while, I think, that should be important as a mediator between closed and open strings.
The constraint can run itself, and it's not fixed.
Well, yeah, that's, I mean. And so here we have a sort of really crucial new recent ingredient, which is Abuzaid's generation criterion for Fukaya categories. So we're going to use a sort of dual version of that, which was considered by Abuzaid with Fukaya, Ota, and Ono. And I think Fukaya had a big hand in the ideas that underpin this, and Biran and Cornet also had some related ideas. But the point is this: to show so if you know that for your chosen subcategory A, the closed open map is injective in the top degree 2n, so QH2n to HH2n, then you conclude that A split generates the Fukaya category. Okay, so that's really a sort of beautiful symplectic geometry result, and that's what we want to apply. The top quantum cohomology is generated by the top power of D. So what we actually want to do here is to show that CO does not kill the top power of D. And then we'll be done. Well, Nick observed in his thesis that CO of D is actually something rather simple. The point is that, I guess I didn't say it, so we weight these holomorphic curves by how many times they intersect the chosen divisor D. You weight them by powers q to the u dot d, like in quantum cohomology. And when D is actually your constraint, then you know exactly how, then you actually know how many times these curves hit D, because they're already encoded for you. And so what it actually tells you is that so CO of D it's basically the derivative with respect to Q of the A infinity structure of the Fukaya category. Okay, so it's a class in the second Hochschild cohomology of this bit of the Fukaya category that's telling you how the structure of that category deforms as a function of Q. Let's turn to the B side, and there's a precise analog, a mirror, to the closed open string map, and that's a version of the Hochschild-Constant-Rosenberg map. So that's a ring isomorphism, in fact, from tangential cohomology to the Hochschild cohomology of the derived category. So there's a long list of names associated with this, starting with Hochschild, Constant, and Rosenberg, but finishing, or at least a relevant, recent relevance is Kolak, van den Berg, Rossi, who sort of show that this is really a ring isomorphism. And one can compute what HKR does to the Kodara-Spencer class theta, and what you get is the categorical analog of the Kodara-Spencer class, which describes how the structure of this category varies as a function of Q, just like we had on the Fukaya side. Well, so we need to use a bit of homological algebra, and in particular, because B split generates the derived category, the restriction map from Hochschild cohomology of the derived category to that of B is an isomorphism. So those are just identical. So you can think of the target of HKR as being the Hochschild cohomology of B. And now we put it together. So we're assuming weak homological mirror symmetry, and now we form this ring map kappa. And the way we do it is this. We use the closed open map to get us to Hochschild cohomology. We use the fact that A is identified with B to say that they have the same Hochschild cohomology. And the Hochschild cohomology of B is the same as that of the whole of the derived category. And then we use the Hochschild-Constant-Rosenberg map in reverse to get back to tangential cohomology. So that's 3 ring maps. Their composite is kappa. Moreover, the distinguished degree 2 elements behave very nicely under these maps. So the class D in here, in quantum H2, maps to the categorical Kodara-Spencer map here, describing how the structure varies in Q. That then maps to the corresponding thing here, which is the HKR image of the actual geometric Kodara-Spencer class here. So consequently, under kappa, D maps to the Kodara-Spencer class. And that's what we crucially use. So we have a ring map kappa, so its effect on D to the n is that it maps to theta to the n, which we've assumed as non-zero. That was our maximal degeneration assumption. And now Abuzaid's criterion kicks in and tells us that A split generates. Okay. So last slide, I think. So at this point, seeing that kappa is an isomorphism is not so complicated in some ways. So kappa is injective in top degree. That's what we just established. Well, it then has to be injective in all degrees because, if it killed some class X, well, there's some sort of essentially Poincaré dual class Y, so that X cup Y is non-zero in top quantum cohomology. Can't happen. So CO is actually an injective map. Then, using ideas from Shiel-Ganatra's thesis, one can deduce that it also has to be surjective, and consequently an isomorphism. So CO is an isomorphism. Okay, that's what we get from Shiel's arguments, roughly, and consequently so is kappa. Okay, so I'm not going to go through the argument that says that you preserve Frobenius traces, which was the third clause. So, but some sort of key ingredients that we're using here are Abuzaid's generation criterion for Fukaya categories, an observation about the role of maximality of degeneration in this story, and we also make some use of recent advances on Hochschild Constant Rosenberg. I might also have added to that we use Shiel-Ganatra's recent ideas, which have to do with the importance of homological smoothness in this setting, in part. And so we're using those ingredients, coupled with homological algebra to get these results. Okay, so thank you. I'll stop there.
Yeah, thank you very much.